Okay, anyway, that was a problem. So hopefully those it doesn't matter. Okay, so let's start today's class then. So so today I'll give you some more. I will talk more about rational form and Jordan form, and we'll see some examples as well how to compute it. So remember, given a vector space and a linear map, vector space over field K and a linear map from V to V, we can find, so rational canonical form says that we can find a basis such that the matrix of this linear map looks like this. Yeah. So of course, if you are given a matrix, you are allowed. So change of basis means you have to do some row operation and corresponding column operation and so on. And using that, you can find. You can do this. You can get to this matrix, and if you do this row operation followed by a corresponding column operation, it doesn't change the linear map. Yeah. So you are in the same. So you are doing a change of basis in some sense. So one can try to find algorithms to do this, cook up this rational canonical form, but those algorithms are a bit complicated and requires computers. But for smaller 3x3 matrix, for instance, or even up to 4x4, maybe one can do it by hand using some more trickery rather than this row operation and column operation. Yeah. So here, for instance, this A1 to A. So as I said, this rational canonical form is unique. So this A1 to AM are determined by this linear map. Yeah. So maybe one can capture what these A1, A2, AM are. So they are invariants. Yeah. So they are called A1 to AM are called invariants, invariant factors, this R mod A1, R mod A2 are called invariant factors, or invariant polynomials. Yeah. So I don't remember the terminology exactly. I think so there is no standard terminology as such, but I think in this book, Dummett and Foote, they call this as invariant polynomials. Yeah. And there was this equivalent version of about matrices with respect to matrices. And then there is a similar Jordan form. And for that, you want the base field to be complex numbers. And then if you are given a linear form, you can again transform it in this particular. So you may not. So you must have seen diagonalize how to diagonalize a matrix. Yeah. Meaning without changing the similarity class, so to speak. So you may not be able to diagonalize all matrix, but you can always get it in this Jordan form. So again, the algorithm. So if you are over complex numbers, you can always get to this form. And remember, if you have this, if you have one form, rational form, you can cook up Jordan form, and from Jordan form, you can also cook up rational form. Yeah. So both direction works. So we know that the two structure theorem are equivalent. So from one you can read the other and so on, because you can write down the invariant factors. Yeah. So if you know each of these guys, each of these blocks, then you know what are the invariant factors. Yeah. So this one will correspond to Cx. Maybe I should write it with the right pen, so that you know this is not the part of the statement. But this one will, for instance, correspond to Cx mod, which factor, what should be in the denominator?
So x minus lambda whole power.
So this is x minus lambda whole power r. Yeah. So here it will be x minus lambda 1 whole power C. So this factor corresponds to saying V is isomorphic to x minus lambda 1 whole power R11. dx sum x minus lambda 1 whole power x rcx mod x minus lambda 1 whole power for r1 2 and so on. Yeah, so this is how you can identify v with some other c vector space. Yeah. And on that c vector space, the action of phi is by multiplication by x. Yeah. So today, so again, how do you get this lambda i's and these ri's is from the linear map is a bit tedious. But if you know a1 to am, or if you know one of these lambda i's and corresponding rij's, then you can get the other one. Yeah. So if you have one set of data, you can get the other set of data. That's not difficult. Okay. But getting one set of data is a bit of an issue. So let's just try to analyze what these invariant factors are. So some of the invariant factors are easy to compute, and that's what we are going to work out today. Okay, and then we'll get to an example. So first of all, if you are given this phi, what is the minimal polynomial of phi, or this linear map phi, whose Jordan form or rational form we are trying to figure out? We want to know what is the minimal polynomial of phi, or what is the characteristic polynomial of phi, or what are the eigenvalues of phi. These are some of the invariants of your linear map. So that should somehow appear in this rational form or Jordan form and so on. Yeah. So first, for instance, minimal polynomial of phi, you can read it out from rational form. Eigenvalues of phi, you can read it out from Jordan form and so on. So let's just see how. Yeah, so note that v is isomorphic to kx mod a1 up to kx mod an. Yeah, if v is this vector space and phi is this linear map and it has rational form like this, then we know that v is isomorphic to this guy. Yeah, this is how the proof went. Right, and we know that a1 divides a2 divides am and so on, where ai's are non-constant monic polynomial. So what is the minimal polynomial of phi? So minimal polynomial of phi, what we'll see is this am. Yeah. So how do you get that? So remember, minimal polynomial of phi is the least is mx is some polynomial m phi x in kx is the least degree monic polynomial such that m phi is the zero endomorphism of phi. Yeah. That is the definition of minimal polynomial of phi. It's the least degree polynomial, least degree monic polynomial. So in particular, it's non-constant. So you can't take phi polynomial to be zero, such that if you plug in phi, then you get the zero endomorphism. So in other words, MAA, that is what is zero. That is the characterization of minimal polynomial. Yeah. So what does that mean? That means so m phi is the zero endomorphism of v. But how does m phi x act on a vector space v? That acts as m phi evaluated at v, and then you evaluate so you get an endomorphism, and then you evaluate at v. Yeah. So saying that this is the zero endomorphism of v, same as saying that m phi x dot v is zero for all v in v. Yeah, because that's how x acts on this vector space. It's by evaluating phi. Yeah, x dot v is phi v. So m phi is the zero endomorphism, means m phi x dot v is zero for all v in v. Does that make sense, guys? This step? Yeah, and that precisely means that the annihilator of v is m phi x. Yeah, and what is the annihilator of the right hand side? Well, to compute the annihilator of the right hand side, we know that am will certainly annihilate it, because a1 divides. So if you take am and multiply with any element of the right hand side, it will become zero, because a1 divides am, a2 divides am, everything divides am, all the denominators here divides am. Yeah. So AM certainly belongs to the annihilator, and suppose you have given an element on the right hand side, and so I want to say that annihilator is exactly AM. So and suppose R is an element of the ring which kills this. So that means um, R dot. So you take uh, so so you consider one bar, so to speak, in the right hand side. Yeah, and if R dot this is 0 in the right hand side, so this is a 0 vector in some so it's like 0 0 0 0 0, then that means that R is in the ideal generated by A1, R is in ideal generated by A2, up to R is in the ideal generated by AM. So that tells you that R is in the ideal generated by AM. Yeah, so that gives us that this is actually an equality. So annihilator of V as an R module. So this is R is as a KX module. Yeah. And the AMX is already monic, so that tells you that AMX is same as MPX. Yeah. So this shows that the minimal polynomial of phi is indeed AMX. Yeah. So the last polynomial, the highest degree polynomial among these AIs, is actually the minimal polynomial of phi. So you can read out the minimal polynomial just from the rational form by just looking at this last block diagonal guy. I mean, the coefficients of the polynomial are all hidden here. Okay, makes sense, everyone? Any questions? Okay. Now, now what about the characteristic polynomial of phi? So we want to know what the characteristic polynomial of R phi is, but let's start with characteristic polynomial of RA. Yeah, and once we know the characteristic polynomial of RA, R phi is block diagonal, so we'll know the characteristic polynomial of R phi. By the way, any guesses on what the characteristic polynomial is going to be? Of R phi?
Yeah, so it should be the product of all these.
Yeah, so it's going to be the product of all the AIs. Yeah. So let's see. So if so for that we'll have to show that characteristic polynomial of RA is just A. Yeah, and then of course that will tell us the characteristic polynomial of R sub phi is RA characteristic polynomial of RA1 times characteristic polynomial of RA2 up to characteristic polynomial of RA. Yeah, because it's block diagonal. Yeah, and characteristic polynomial multiplies. It's just the determinant of something. So what is the characteristic polynomial of RA? RA looks like this matrix, yeah. So xi minus determinant of xi minus RA is precisely, so you'll get x in the diagonal and minus 1 in so and RA here you had ones in RA, so that becomes minus 1, and these were minus b0 to the minus bn minus 1, so they become plus, so you get this. So you are trying to end zeros elsewhere. So we want to calculate the determinant of this matrix, so you expand by the last column. Yeah, and I'll start from below because I know that the coefficient of this guy has to be positive. Yeah, so x plus bn minus 1 times the determinant of this matrix, but this matrix is a diagonal matrix. Yeah, not a diagonal matrix, it's a lower triangular matrix, so there is nothing on the upper part and there is minus 1 in the just below the diagonal. But upper triangular matrix is the determinant is just the product of the diagonal entries. Yeah, and then bn minus 2, so that will come with a negative coefficient, yeah, times the determinant of that cofactor. So you remove the last column always and the second last row. So the matrix you will get is this guy. So x in the diagonal, minus ones in the just below the diagonal, and then you have to move this this last column up. So what you get is in the last row up. So in the last row you get minus one in the so 0 0 0 minus 1. This is what you get. Yeah, so if you take the product of so again this is a lower triangular matrix. So just you just have to take the to calculate sorry, it's a determinant of this guy. Yeah. So all these are determinant. So the determinant of this guy is again x power n minus. So this is a matrix of size n minus 1, and there are n minus 2 x's in the diagonal. So what you get is x power n minus 2 with a negative sign. So it becomes plus, yeah, and so on. So so I've done bn minus 3 as well, and you can see what you get is yeah. So now what you get is somewhat different. So this is this part. So here, for instance, you somehow there was only one entry, so it didn't matter. So this is always an lower triangular matrix, and then you get a second block like this. So similarly, what you'll get is a lower triangular matrix, and then another block, which will be an upper triangular matrix. Okay, and then zeros in this. So the determinant of this guy is the determinant of this upper triangular times the determinant of this lower triangular. Sorry, determinant of this lower triangular matrix times the determinant of the smaller upper triangular block, because the off diagonals are 0. Yeah. So this result, I suppose, you must have seen in your linear algebra. So the determinant of this block upper this bigger block is x power n minus 2, and the determinant of this is going to depend upon how many minus 1s are there in this. So for n minus 3 there are 2 minus 1s, so you get plus 1. Okay, so you can just verify. So maybe if it's not satisfactory, you do one more step, and you'll see this is what the pattern is. So you get that. So again, you get x power n minus 2, and with positive n minus 3. Yeah. B n minus 3 with positive coefficient. So if you evaluate this, you get, so you expand this out. So you get x power n, bn minus 1, x power n minus 1, plus bn minus 2, x power n minus 2, bn minus 3, x power n, plus bn minus 3, x power n minus 3, and so on. Eventually, you'll get b0. Everything will become on plus or yeah, plus b. So somehow this plus and minus things are there alternating, but it gets cancelled by the number of minus ones you'll get in this small block. So you'll get all plus, yeah, which is same as ax. Yeah. So you get that the characteristic polynomial of Ra is ax, and hence the characteristic polynomial of Rphi is the product of this invariant polynomials. Okay. Any questions? Okay. Okay, so if there are no questions, so you know what the characteristic polynomial of Rphi is. So we had started with these 3 questions. So minimal polynomial, you know, characteristic polynomial, you know, just by looking at the rational form, you can get it. So that's one of the and conversely, if you well, not conversely. So you just knowing the minimal and characteristic polynomial won't give you the rational form. You need all the invariant factors. So as I said, one of the invariant factor is easy to compute, which is the minimal polynomial. But and you know how to compute the product of the invariant factors, but individual invariant factors are difficult to compute. So I don't know how one would compute, other than the fact that other than finding an algorithm to write the to compute the rational form using some row operation and column operation, and then working it out, or maybe Jordan Yeah, so maybe that, but so there will be an algorithm because it sort of doesn't use um, yeah, so because you don't have to factor any polynomial and stuff. So rational form, there has to be an algorithm. It may be a complicated and tiresome algorithm, but there has to be an algorithm. Yeah. Okay, so finally, eigenvalues. So for that, of course, you look at the Jordan form. Yeah. So eigenvalue of phi are this lambda 1 to lambda m of this Jordan form. Yeah. Because this is how Jordan form look like, and the eigenvalue of this matrix we know, since it's an lower triangular matrix, is just lambda, and we also know with what multiplicity each eigenvalue will come if we know the Jordan form of the linear map. Okay. Any questions? By the way, so one can also ask what is the uh, characteristic polynomial of these small factors, yeah, of this Jordan block. So here, so what is, by the way, what is the minimal polynomial of Ra? Minimal polynomial of Ra?
Be A itself, because that's the only invariant factor.
Yeah, so minimal polynomial of Ra is A. Yeah, because I mean, you consider Ra as the linear map from some other vector space to itself, and then of course its rational form is itself, yeah, because it is in rational form, and then of course that tells you that there's only one invariant polynomial, one invariant factor. So so that vector space you can write it as kx mod ax. Yeah. So the minimal polynomial is just going to be, so here minimal polynomial of Ra is A, and characteristic polynomial is also A. So this is sort of okay. Yeah. But what about minimal? Yeah, so maybe before doing this example, what about is AX? Let's just shut this down. What about minimal polynomial and characteristic polynomial? So characteristic polynomial is straightforward, and so should be minimal polynomial. J lambda R. So what will be the minimal polynomial? Or maybe what is the characteristic polynomial? First, the characteristic polynomial. If j lambda is this guy, then it's just x minus lambda whole power r. Yeah, that is because it's a lower triangular matrix. So characteristic polynomial is same, is simpler to calculate. So it's x minus lambda whole power r. But this is also the minimal polynomial. This is also the minimal polynomial. Okay. So here also the characteristic polynomial and minimal polynomial are same. So this again you can just check directly as well. So if you subtract j lambda minus lambda I, then you get zeros on the diagonal and ones on just below the diagonal. So if you take any power less than r, it won't be zero. You have to go all the way to rth power to make this zero. Yeah? And then you can use the definition of minimal polynomial. So minimal polynomial has to be a factor of x minus lambda power r. And you can see that x minus lambda power r minus 1 is not going to be the minimal polynomial. That is, if you plug in j lambda r here, then you won't get 0. Okay, so again for both these basic blocks. And another way is to think of it as a block in some sense. Yeah. So so you can't. It's already a cyclic module of a smallest possible block. So it has its minimal polynomial and characteristic polynomial have to be same. Okay, so let's do one example now. So how do you compute? Jordan and Jordan form or rational canonical form of a matrix. Yeah. So let's try to do it by hand first. Yeah. So suppose V is this C3 and A is some matrix. 1, 2, 1, 2, 0, 3, 4, 0, and 0, 0, 2. Okay. So of course, then we know that V is a CX module. Yeah. And on which X acts by X dot V is AV. Yeah. So we know V is going to be, by structure theorem, is going to be isomorphic to something like this. Yeah. So there could be three factors, 2 factors, or 1 factor. There can't be more than 3 factors. Yeah, because each of these factors is at least 1 dimensional and V is 3 dimensional. So it has to be one of these 3. Yeah. So so maybe you can rule out some possibilities. So if it were, it can't be this, yeah, because somehow if it was this, then A must be a diagonal matrix, and maybe one can argue that A is not a diagonal matrix. Okay. No, A will be a scalar. If it was this, yeah. So how do I throw out this possibility? A could be a diagonal matrix, but how do I throw out this possibilities? This possibility. So what happens if it is this? So so it depends upon the degree of AIs. Yeah. So the degree of A1 is going to be less equals degree of A2, and they all have to be such that the dimension add up to 3. Yeah. So if it is this, then all these AIs must have the same degree and must be at most. So if the degree goes up, then the dimension of this factor is same as the degree of this polynomial. So all of this must be degree 1. Then only it's possible to have this. So suppose all of them are degree 1, then of course A1 equals A2 equals A3, because they all divide each other. A1 divides A2 divides A3, and they are all degree 1. So it's going to be this, and then the minimal polynomial is just a linear thing, and the so X minus some lambda annihilates A, which means annihilates the vector space. So that means minimal polynomial of A is X minus lambda. And X is X minus lambda, which implies A must be lambda times I. Yeah, there's no other possibility. But we know that A is not lambda times I. Yeah. So so this you can rule out, but it's not so easy to rule out these two. Yeah. So which one will it be? Whether it's CX mod A1X or it's this. Yeah. So since I have taken a matrix which is somewhat random, it has it should be this one. If you want to guess. This is something special has happened. Yeah. So that's when you get these you get 2 factors. If for a general matrix you'll get only 1 factor. For a general matrix, you know that the characteristic polynomial and the minimal polynomial are same. Yeah. So there are no other factors. So there's only 1 factor. But for some special matrix, you can have general polynomial. The characteristic polynomial and minimal polynomial are different. So to check whether these two are same or not, you just have to calculate the minimal polynomial and the characteristic polynomial. So that is the way one does it. You can't really realistically try to find some. I mean, you can't use the algorithm suggested in the proof of this structure theorem. Yeah, so that's somewhat existential kind of algorithm. You can use algorithm directly by this row operation, column operation, but not the proof. Yeah. So let's try to calculate. So we want to know the invariant factors. Yeah. So first, let's try to calculate the characteristic polynomial and minimal polynomial of A. So what is the characteristic polynomial of A? Okay. So I didn't do the calculation, but so x minus 1 minus 2 0 minus 3x minus 4 0 0 0 minus 2. So it's determinant of this guy. Yeah, which is so this is x minus 2. So so x minus 2 is one of the factors. So I'll not try to expand it completely, but here we get x minus 1 times x minus 4 minus 6. Yeah. So I don't know if it can be factored completely. So x minus 2 x squared minus 5x plus 4 minus 6. So most likely not, because I just took something random. So x squared minus 5x minus 2. Yeah, so I don't think this can be factored in complex numbers, but not in integers. So let's just look at what the roots are. Yeah, so at least we can do this. So 5 plus minus square root of b square minus 5 is 4ac. So 24. What will be there? 25 minus 33, is it?
Yes.
Okay. So over 2. So we see that we get 3 different roots. So this, so what will be the minimal polynomial of A? So it can't be a proper factor of characteristic polynomial, yeah, because they have the same root. So we get that the characteristic minimal polynomial and so sorry. So this may look misleading. So if it happens this, then this happens, and then this happens. Yeah. So if this will imply this contradiction. So maybe I should put so that when I upload it, this doesn't look garbage. Okay. So this was to say that this can't happen. Yeah. So this argument. Okay. So minimal polynomial and characteristic polynomial are same. So that tells us, so from here we can conclude that A3 is same as CHAX is same as MAX. Yeah. So what is the rational canonical form then? So to calculate the rational canonical form, anyway, we'll have to know the coefficient of this polynomial, all the coefficients. So we may as well multiply this. Yeah. So what do we get? X cube minus 5x squared minus 2x. So I'm a bit slow in multiplying it, polynomials. So minus 2x squared plus 10x plus 4, yeah, which is x cube minus 7x squared plus 8x plus 4. Yeah, so from here you can get the rational form. So it's going to be a 3 by 3 matrix. So 0 0 minus 1 minus 1 and 0 here, 0 here, and then this last one is just the coefficient of this guy. Yeah, so 7 minus 8, 4. Okay, so this is the rational form of A. Yeah, rational form of A. So though, I mean, if someone gives you this matrix,
Excuse me, sir.
yeah.
Yeah, that will be minus 4, no? Oh, I think you have written it's plus 4 in that. Minus 4 minus at 7. Yes.
Oh, this should be plus 4. Yeah, this is what you're saying.
Yes, sir.
Good. Yeah.
So
this
in
is
the matrix, that's minus 4.
minus 4. Yeah. Thanks. Yeah, in spite of doing slow, I made a mistake. Yeah. So so you have to do this carefully. But this is how you get the so this tells you what the rational form will look like.
Excuse me, sir. So
Yeah.
why is it -1 over here?
Where? Oh, it should
Below.
yeah. Sorry. Yeah, this is what you're saying.
Yes, sir. Thank you, sir.
Yeah. This is plus 1. Okay. So this is 1. This is 0. Yeah. So this is the rational. This is how the rational form. So yeah. So just remember these. Rational form looks like this. Yeah. Zeros in the diagonal, ones just below the diagonal, and then. So I'm just trying to copy that algorithm. Yeah. So you get this is the rational form. Okay, and if someone gives you a matrix which looks like a rational, which looks like in a rational form, you can just write down its characteristic and minimal polynomial. In fact, you can write down all the invariant factors as well. Okay. And what about the Jordan form of this matrix?
So just the diagonal with the eigenvalues.
Yeah, so here it is actually diagonalizable because the characteristic polynomial and the minimal polynomial are same. This actually is diagonalizable, so you don't get something different from. So and then there is no particular order you have to choose because the uniqueness here is up to permutation of the eigenvalues. So Jordan form is just the diagonal matrix. But you can get so if there were multiple roots, so if one had chosen some multiple roots, then you could get some different Jordan form. So the only way I can do that is not by writing random matrices, but to start with something, some matrix like that. Yeah. Any questions? So this is essentially all I have for today. So you can practice some more of this. Some more problems on this. So I think I didn't assign any homework problem, but on this thing. So I'll put down I'll put up some homework problem which you can try it out before. But so it will be only on my web page. Yeah. So since I'm not collecting it, I won't put it on the Moodle. So I'll put it on my web page, and maybe I'll also email you so that you can get it. Okay. So are there any questions?
Sir, will we have finding the rational Jordan canonical form for larger matrices like the 4x4 and all the exam on?
I won't ask you something which is computationally too intensive. Yeah.
Okay, sir.
Because yeah, so I'm in something which you can do it without much computation is the only thing I'll ask. Okay. Any other question?
So the problems, could you please give a hint for this one? So it's from another past paper. Uh, you had said that one. We need to check whether or not all prime ideals are maximal
Mm-hmm.
in the following ring. Uh, the ring is zx mod 2x square minus 10.
So this is some question. Maybe, yeah, anyway, I can put it here. Zx
Mod 2x square minus 10.
2x square minus 10. This is the ring, and you want to know whether every prime ideal is maximal.
Yes, sir.
Okay, so first of all, yeah, so this 2 times x square minus 5. Yes, sorry, x square minus 5. So it looks like this will be the case. So every non-zero prime ideal, yeah.
Yes, sir. The non-zero prime ideal.
So no, so this is not true, yeah, because of course it's not an integral domain, yeah. So 0 is not a prime ideal. So there are of course two prime ideals. One is the prime ideal generated by 2.
Yes, sir.
Yeah, so you can check that the 2 bar consider the ideal generated by 2 in Zx, yeah. So let's call this this ideal I, yeah. So I is contained in 2, yeah, and 2 is a prime ideal in Zx. So that tells you that 2 mod I is an ideal in this ring R, and it's a prime ideal, yeah.
Yes.
And this is of course not maximal in R because 2 come so for instance you can take 2 comma x square minus 5, yeah. This is this will be this also contains I, yeah, obviously because it in fact contains 2, yeah, and this you can show is a maximal ideal. So either okay, let me just think about it. X square minus 5 so this yeah, so maybe not x square minus 5, but x square minus 5 is sort of reduced. So this is not a maximal ideal, unfortunately. 2 comma x square minus 5 is same as 2 comma x square minus 1, yeah, and x square minus 1 is x minus 1 x plus 1, yeah. So not this one, but you can check that. So one has to be a little careful, yeah. But you can check, for instance, that yeah. Yeah. 2 comma x minus 1 is a proper ideal of this guy Zx, okay, and so of course it is a proper ideal of Zx, yeah, that of course you are convinced, right? Because if you go mod this is just z2 adjoint x mod x minus 1, and it is and it's so you can see that if you go mod this you get z mod 2, yeah, so it's a maximal ideal.
Yes, sir.
Okay, so not every prime ideal is maximal.
Okay, sir.
If you remove this factor 2, then it becomes, yeah, so the I think x square minus 5, yeah. So the problem is with this factor 2. So if you had a irreducible polynomial here, then it works out that every here the problem is non-zero non-zero ideal is not a prime ideal, yeah. So there will be more than one.
Okay, so in any case, when zero ideal is not a prime ideal, this property would fail.
Yeah, certainly. I mean, unless the sometimes if you take meaning it's not that zero ideal is not a prime ideal means every prime then prime ideal every maximal ideal can't be prime ideal is not true. So of course you can look at qx mod x square, yeah, or just z mod 4. So this in this ring, in these two rings, every prime ideal is maximal.
Yes.
Okay. But so it's something to do with dimension, so which is too early for me to explain. So maybe you'll see it in commutative. This is a one-dimensional ring, but somehow so you expect prime ideals to be maximum, every non-zero prime ideal to be maximal, but it's not an integral domain. So if it was one-dimensional integral domain, then every non-zero prime ideal is maximal.
Okay, sir.
Okay.
Yes, sir.
Any other question?
Yes, sir. Thank you, sir.
You're welcome. Any other question?
Excuse
Okay,
me,
so
sir.
yeah.
This is Sonali. Have you received my mail?
Yeah, so I'll respond. So is this some sort of formal thing or is it some informal thing?
No. So I just want to learn further. Actually, I have done it before also, but at that time we couldn't proceed as we didn't have a ring theory course.
Okay.
So, like to learn more, I have to do the ring theory course first. That's what Sarnam told me that time. So I just want to learn ahead of that
Yeah.
what I have done.
Yeah, so I'll respond to you separately. Yeah, but let me just make some observation for those who are still around in this class. So if it was not a pandemic year, this kind of circumstances, there are a few things more I would have done. So if you want to study a little more on this topic, these are the things one should immediately look at. So there's something called tensor product of modules. So mostly, so basically on modules, yeah, these are the things I would have done. And then exact sequences, so maybe this should probably go here. I don't know, exact sequence, but it doesn't matter. They are not really related. You can first define tensor module product and then think about exact sequence of modules. Okay, and then certainly done how these, so maybe projective modules and home and how it projective modules. So these things I would have done, and then if you want to read further, there is something called flat modules, and so flat modules, I'm not sure I do it in undergraduate, but if time permits, one can see flat modules. Is all the data material are there, and then how this how tensoring, how home behaves with exact sequences. So this is so all these things are there in. So home is a sort what is called a functor. So, but anyway, so these things are there in Damit and Foot, and also tensor with some module. Okay, so these are some things which you can read up after. So during your winter break when there's no semester going on, and if you're interested in algebra. Okay, so these are some, and you can always, if you're reading things and you have some questions, feel free to email me. I'll be happy to answer them. Okay. Okay, so I guess that's about it. Best of luck for the finals, and I hope everyone is safe and sound at their home. And let's hope this ends sooner and we are back to our classes. It's a bit impersonal to teach this way. Yeah, I don't get to see faces, so I don't know how many of you are understanding and how many of you aren't. But I hope this course made sense. And but anyway, if you have questions about anything about this course or something, you can email me. I'll try to help you out if I can. Okay. So maybe I'll end recording and.